In this video I look at an amplifier by use of interferometry. The amplifier is the device under test here. I have a signal generator or a good oscillator from Wenzel. It gives 13 dBm. I add 6 dB and then there is a hybrid and a 50 ohm resistor. That splits the signal into two equal parts. In one leg I have possibilities to adjust phase and amplitude, both continuous and in steps. And in the other leg I have this dual switch which can put this wire and that wire to 50 ohm resistors or connect through. Then there is an attenuator, the device, and another attenuator. And since this is an amplifier, I can set the attenuation to compensate for the gain, here or here. And the power that will be seen by the amplifier will then be different depending on how these attenuators are set. Then the two signals, this one and that one, go into a hybrid. And the hybrid has a difference output and a summation output. The summation output is first terminated with an attenuator, so I know that it is terminated in 50 ohms. Then there is a gain block, 20 dB, to get a good signal for the oscilloscope to use as a trigger input. The difference is going first into a coupler, where I can see the level that goes this way. And the level comes here, 9 dB attenuated. First there is attenuator, and then there is a gain block, and a low-pass filter, and the oscilloscope. The procedure is I switch off the signal here, then I have one leg this way, and I set the desired attenuation. Let's say I want to suppress the carrier by 40 decibels. So I set 40 decibels here, and then I mark the level I see on the oscilloscope. Then I switch in the signal through here and set the phase and amplitude to make the signal to the same position on the oscilloscope when this attenuation is set to 0. That means I have the signal going through the setting that I had on this oscillator so much weaker. And that goes into the signal analyzer, and the idea is it's only the carrier and the noise sidebands from this signal source that is attenuated, while the noise produced here comes at its full level. So I enhance the sideband noise and make it easier to see it on the signal analyzer. This is the amplifier I want to look at. It's the amplifier in the two crystal oscillator I have been investigating in the previous video, nerds85, and also in some previous ones before that. What I do is I cut here, so there is no signal coming through the crystal, and then I inject through a 100 pF capacitor into this point. That's the low impedance input of the FET grounded base amplifier. Input impedance about 10 ohms here. And then I have this input connected to the usual place, the feedback input, because on the feedback input there is a ferrite core that could generate noise that could go back this way and enter this output. Here is the output that goes in the measurement. It's the output of the device under test. I have set the switch to Z0, which means that one of the legs in the interferometer is switched off, So what I see now is the test signal I am sending into the interferometer. And here is the phase noise. That's the performance of the Wenzel oscillator. The amplifier does not contribute significantly. And I save this as well as some other plots of the same measurements for further use. The level on the oscilloscope is now 10 volts peak to peak. I changed the attenuator by 40 decibels, like that, and the signal becomes much weaker. At 10 volts the amplifier is a bit saturated, but now it is certainly in the linear range. And I set this level. And this is what I want to achieve when running the interferometer. So I set the switch here to 0, and then I see a very weak signal, and I restore full signal here, and then the signal is strong. So I change the settings in the interferometer, something like that, and then the continuous. That was a minimum from the amplitude adjustment, and then I go for the phase adjustment, and the amplitude adjustment again, and I want this level. And here I have a 40 decibels weaker carrier. These two attenuators are on the input of the two-channel receiver that makes my analyzer system, and they are set on 20 or 22 decibels. So I turn up the gain by 20 decibels here. And this should not saturate the receiver. This should still have a margin of about 20 dB. Since the carrier is suppressed by 40 decibels. And as you can see, the amplitude margin is about 21 decibels now. And I have to wait for quite some time before I get the result here. It's obvious that I have some noise that is added from the amplifier under test, particularly close to the carrier here. But also out here I can see the noise level is a little higher, as well as here, of course. And then there is some kind of a spur that shows up. I don't know the origin of that. And striking is that there is no need of correlation anymore. The yellow trace, and which is the correlated spectrum, and the signal in the two channels is the same, and the same as the correlation spectrum. So this is really the noise added by the amplifier I'm testing. The phase noise, that is. The amplitude noise is much lower, and it is below the noise floor in the channel, so I have to wait for the correlation result. It will take some time, and maybe here there is some contribution from the signal of the oscillator. I don't know. At frequencies above about 10 Hz here, performance is limited by the sound card noise. It is the center, the DC noise here, that comes as noise here. But there is a 21 dB amplitude margin, So I should add about 20 decibels of amplification in front of the analyzer, or rather I should add 20 dB after the hybrid that splits the signal into two in the analyzer. Phase noise is a little better, but there is a problem here. You can see it goes down. It is a contribution from noise in the sound card, correlated noise in the sound card at close to DC. And that should also improve if I add gain in front of the system. I have increased the gain by 20 decibels now. And as you can see, noise is much stronger. I have to change the color scale here from 20 to 40 to hopefully get the same thing back. I have to wait for a while because there is various forms of noise while I was connecting and disconnecting different attenuators to set the gain to what I wanted. It is immediately clear, however, that now I have a much better measurement of the phase noise. And probably also the amplitude noise will look better. Like this. And we can see that the amplifier in channel 1 has amplitude noise. That's not so surprising because it's an MMIC which is known to be a bit noisy. I found a better amplifier for channel 1. It's a bipolar, while channel 2, like the much worse previous channel 1, were MMICs. SPF 5043 and PSA4 5043. That's the one I'm still using. But this is amplitude noise and I'm mainly interested in phase noise, so I think I will leave it like this. Here is the phase noise after only 8 minutes. It seems I can see it pretty well now. But perhaps at very close range there could be a contribution from the signal, the Wenzel oscillator. I will look at that. These are the numbers I see with 40 dB carrier suppression. These are the numbers I see with 40 dB carrier suppression. Differences are rather small and I get slightly degraded values here and here. That's because with 50 dB carrier suppression, the stability is no longer perfect. The carrier has become a little weaker, and that makes the noise a little bit higher with respect to the carrier. So long measurement times are more difficult now. This time the level has been stable, and I have collected for 45 minutes 270 spectra, so I get a fairly smooth curve. This is 1 dB per division, and I will make a table out of these points. It's obvious I have to avoid the region from about 20 Hz up to about 50 Hz because of the negative correlation from the sound card, the zero frequency there. Amplitude noise in white, like this, and this is an artifact due to the zero frequency, while phase noise is something like that, with this an artifact. Unfortunately, I cannot move the 10 MHz oscillators very far from each other, so I cannot avoid this zero frequency. Anyway, amplitude noise is fairly weak. I don't think I have to worry about it. And here I see the correlation. Phase noise and amplitude noise are not correlated above about 400 Hz, and very little down to about here somewhere. And this shape clearly indicates that something funny is going on here, and that's of course related to the zero frequency here. So I cannot trust this region. Here is the curve I get, like this. And the power output from the amplifier is 21.2 dBm. I have tried 3 different power levels, 24 dBm, 21 and 18, 3 dB steps. At high power here, noise is lower at half an hertz, or also at 2 hertz, but at about 5 hertz the noise is the same for all the power levels, and at 15 hertz noise is degraded when power is increased. So the curves cross all of them at this point, and then at very high offsets, well, 500 hertz, the lower power comes closer to its flat noise, so it is worse, while the medium power is here. The medium power is best, and high or low power is a little bit not so good. Now, this is difficult to measure, so these points are a little bit uncertain. But this is significant and obvious that more power creates noise somewhere, and an odd phenomenon makes noise lower at very close frequencies, down at 1 hertz from the carrier, and the difference for a 6 decibels change of the power is from here to here. That's 5 decibels, so it is a large effect. What I want to achieve is something like a line here, like this. I don't think I can hope for more than 5 decibels better than the red line, which is a very good oscillator you can buy on the market. But I want to keep it as good as that, all the way down to the flat noise floor at 185 or something. That would be down here. At the intermediate range, 15 hertz or so, I am about 10 decibels off from what I want. But very close, there seems to be no problem. Peculiar, I think. To try to understand how noise comes into the amplifier, I am now looking only at the first stage, still injecting through 100 pf to the sources, but I take out the signal on the first transformer, on the secondary of it. I should load here by about 120 ohms to get the normal currents and voltages in this transformer, but I am connecting 50 ohms directly here to start with. What I see is unexpected. The noise at 0.5 hertz is here. It is above minus 120. That's something like 15 decibels degraded as compared to before. But at a little bit higher offsets, let's say 3 hertz here, it is at minus 150. And that's more in line with what one would expect. Now, I am running the box without the screen, so it's completely open, and I put the screen back. This made a big difference, easiest seen in the waterfall here, but of course also here, something like more than 20 decibels. And I did not even tighten the screws, which is usually necessary when the problem is electromagnetic interference. So I do something a little bit odd. I replace the screen with some foam plastic, which is certainly not affecting the electromagnetic field here. And to make sure it is tight, I place a thin book on top of it, like that. And this has not changed the electromagnetic situation inside the box. Now, this is about the same as with the screen. So my conclusion is there is low frequency noise in the room here, probably from the various fans that are in power supplies or in the computer or oscilloscope or wherever. I don't hear much of it. Maybe you can hear through this recording there is a little noise in the background, but it isn't very strong, although it has a dramatic effect at frequencies below 2 Hz. I will first change parameters on the lean rod to make this phenomenon more visible, faster and easier. Here is the main spectrum of lean rod at a resolution of about 0.1 Hz. And now I remove this. And then I have to wait. 0.1 Hz, that's 10 seconds. So it takes time. But it is faster than the other procedures I have been using for sideband noise evaluation, because there is only one buffer to fill. And here we can see the close range noise, and it's very clearly visible. So I will do some experiments to see if I can find what is vibrating in a chaotic way. I will use this, where do you see that this is a plastic tube. I will use that to blow gently on various parts in the box to see if I can see something particularly sensitive. Well, indeed I can see clear effects of blowing gently near the components. This is in one position and that is a different position on the first coil, the big toroid, and this was on the transistors and the 100 pF capacitor hanging close to them. And it seems I can set a faster waterfall, because this will be easily visible also on a faster screen. I have not been able to find out what is the cause of this very low frequency noise that is acoustically coupled into the box. So when I remove this, I get very much the same as before, after the appropriate waiting time. And here it comes, as you can see. And I have to set a very slow bandwidth of about 0.1 Hz to see this well. So I have to live with it and just remember to put the screen back and maybe look for this some other time. But while doing investigations I found a problem, and that's here. this fuse that I have to protect the unit from short circuits, because I have about 1 farad of my electrolytic capacitors on the other side of the fuse. So a short will make almost anything explode. Anything that is not a big enough resistor, that is. But I found that when moving here, I saw instabilities on the oscilloscope. So I will clean that fuse, and maybe this will contribute to an improvement in the future. I'm now running with 50 decibels of carrier suppression in the interferometer, and I have added 50 decibels of gain to compensate, to lift the noise floor and put the carrier close to the saturation point. And I have changed the system. I am now using the 2 SDR IP receivers rather than the sound card to avoid the problem with DC frequencies into the sound card. And here is what I see up to about 400 Hertz. Then there is an artifact in LINRA that bends the curve artificially downwards by 0.2 decibels or something like that. And there is 1 dB per division here. And here is what it looks like at a close range. 0.5 Hertz. You can see the red dots here. That's the imaginary part. It's far down. And as you can see also, the correlation spectrum and the current direct measurement, they fall on the same curve. But there are 1000 averages for the correlation and only 50 for the uncorrelated, the direct spectra from the receivers. I will take down the numbers with the decimal to save this and compare with what I get when I made some little modification on the unit. The data points come on a perfect straight line from 2 Hz up to about 70 Hz. The deviation is a small fraction of a decibel, but the curve bends towards 0.5 Hz and also above 70 Hz. And this I think is natural. This I think is odd. Maybe there is a problem with the measurement setup. I really don't know. I have modified the output like this. 100 ohms in series and 47 ohms to ground. To have an impedance in this point for the signal analyzer to see about 50 ohms, because here is a high impedance. And this point is now loaded by about 125 ohms, which is about what it is when running into the transformer here. And I will see whether this makes a difference or not. Presumably the voltage across this coil is going to be higher, as well as the AC voltage on the drains of the FETs. Here is what I have. I made first this measurement with a 50 ohm resistor. That's the test system, loading the secondary winding on the iron powder core. And this next experiment with 100 ohms in series and 47 ohms in parallel with the measurement system. The current here, I1, has to be very similar to the current here, because a high impedance is a current source. Now the voltage across this 50 ohm resistor is going to be half, because half the current is going here. Half the current means half the voltage. Half the voltage means 4 times lower power. U squared over R. So what I find that the voltage here, which is the voltage on the core, is going to be the voltage drop over 125 ohms, while it was here just the voltage drop over 50 ohms. So the ratio is 125 over 50, that's 2.5 times. So the power on the core is 4 decibels higher now as compared to the original measurement here. So the next experiment is to run this configuration with 4 decibels less input power. Since I know that the interesting region is here, around 20 Hz, where I have a difference of about 8 decibels, I can set much faster parameters in Linearad to get the result very much quicker. Now, with only 4 decibels lower power, I can see at 20 Hz already after 2.5 minutes that the level is 105 on the scale. That means minus 155 decibels per hertz, that is. 155 at 20 Hz comes here. That is about 2 decibels below what I had before. So the main noise source is elsewhere. I have switched off the power supply, which means that this transistor is now a very low ohm resistor from source to drain. So this 100 pF capacitor goes directly to this transformer, which will be far from tuned. So this capacitor makes no harm when I connect a wire from here to here and break up this connection. This way I can measure the noise from these two resistors with very little chance of having noise from the transistors or the toroid. Here is what the screen looks like after 5 minutes at 20 Hz, something like minus 172 dBc per Hertz. And the power level in the resistors is similar to what I had before. Minus 172 at 20 Hz comes down here. And maybe it is not those resistors, it could be the attenuators I have in the interferometers, or maybe something else. But anyway, the problem I see is not those resistors. I have disconnected the FETs, and now I'm injecting the signal through 10 pF up on top of the coil here. And this capacitor has been there all the time, but I didn't remember to show it in the diagram before. And I have connected back this arrangement. So now I'm investigating only the iron powder core. It's from T50, and I cannot see that anymore. T50 material 6. I don't have to wait long until I see that the noise floor is below minus 124 or something like that. Obviously, the problem is not the transformer. I have placed a step-up transformer here, 4 windings of 15 turns, quadrifilar wires on a T50 core material 6, the same core as here. And still 10 pF as a coupling capacitor. I can get now 25 volts peak to peak in this point. That's more than I can ever assume to get from the FETs. And then I have still these resistors here, so it is loaded as if I had this transformer and the amplifier in place. What I see here at 20 Hz is minus 128. That is minus 178 dBc per Hertz. So even at this very high level on the transformer, I see no noise from it. That is, no phase noise. Now I have switched for amplitude noise and it looks very much the same. So the core is more or less ideal, it seems. Here is amplitude noise and phase noise in the same diagram, and there is a small difference, 4 decibels at 400 Hz approximately. I can see that the noise is correlated and it's phase shifted by 90 degrees. The phase shifted component is 50%. So they have a common origin, these AM noise and phase noise. I'm still using the step-up transformer to send the signal in here, coupled with 10 PF into this transformer, and the FETs here are disconnected. But I have reconnected this amplifier, and it is in all respects exactly the same as it was when I was using it in the oscillator. And this capacitor has been there all the time, but I forgot to put it here in the schematic diagram. I have this for maximum, and then the output power is 220 milliwatts. There has been an intermittent noise problem here. To fix that, I have removed one of the attenuators in the device under test leg, the one in front of the box, and I have turned the knob up and down several times on the output attenuator. And that seems to have helped. The noise I see after 1 minute only is around here. That is minus 124, means minus 174 dBc per hertz at 20 hertz offset. So this indicates that the amplifier is very low noise. As it turns out, the problem was fixed for a short time only, from here to here. Now I have removed both attenuators. I only have the switch in place. The switch is also an attenuator, and the 10 decibels is enough in this situation. So now I have to wait for a while. Well, I can already see at 20 Hertz it says minus 125 or so. At 200 Hertz offset, phase noise is minus 186, amplitude is minus 180, and phase and amplitude noise are nearly uncorrelated, so they come from different sources now. And the noise close to the carrier, it seems the poor connection is no longer there. Attenuators are sometimes a little bit risky to use. At close range, phase noise and amplitude noise are fairly similar. Phase noise minus 175 and amplitude 171. Also at close range, the correlation between amplitude noise and phase noise is small. The real part is very close to zero, and the imaginary part means 90 degrees phase shifted between AM and phase modulation. This is also fairly weak, something like 20% or so. In order to see whether DC current through the toroid makes a difference, I have arranged like this, still using the step-up transformer, but now it is directly coupled to this toroid, which is fed by 16 volts here. So with this resistor the current is about 100 milliamps. That's the same current as I have from the 6 transistors or have had previously. And now I'm looking at the noise here. As it turns out, the signal level is lower because the capacitor here used the fact that this is resonant. But now it is just hard coupled to the step-up transformer. So it's about 5 decibels less, but still it's a substantial signal. And since levels of the noise have been so low, if there is a problem, I should see it also at a little lower power output. There is no significant difference. 20 Hz noise at about minus 175 phase noise. And I look at the amplitude noise, and it comes at minus 173 or close to that. I have changed parameters in order to have a look very close to the carrier. And at half an hertz I see 100 means minus 150 dBc per hertz. And at 1 hertz something like minus 155, and 2 hertz minus 160. So there is no special things going on very close to the carrier. I have rearranged the interferometer like this, the device under test directly on the hybrid, and then the combined stepped attenuator and 50 ohm switch, and then the hybrid again, to avoid untested attenuators. The attenuator in here I have tested long ago and marked those positions which are not really okay, and the same for attenuators here. So I can avoid any combination where this one and that one is on a noisy position. In order to make the amplitudes suitable, I have changed this capacitor to 18 pF. Otherwise, this is the same as the initial test of the amplifier. At 20 Hz offset, I now see minus 156 dBc per Hertz. I have increased this resistor, the source resistor for the FETs here, from 11 to 27 ohms. This made a small improvement, 20 Hz. Here it's more like minus 158 now, so 2 decibels better. I forgot to retune this capacitor. It made a very small difference on the amplitude, about 0.1 decibel, or even less than that. But it had a very large effect on the sideband noise. It is now minus 154 only. That's a problem I didn't really expect. When I put 47 kiloohms across this transformer primary winding, the output voltage is reduced by a factor 1.48, and some simple mathematics tells me then that the unknown resistor, that is the impedance here, X, is 2.2 kiloohms. And that is exactly what I thought that I wanted, because this will optimize gain and still keep a good Q on the crystal. But it gives, obviously, phase noise. And I didn't know that. With a 4.7 kiloohm resistor in place, at 20 Hz I see minus 159.5 dBc per Hertz. So that's much better. That is the point here. As is now expected, I find that the 2.2 kiloohm resistor from here to here reduces the output at this point by 6 decibels. The phase noise at 20 Hz is now close to minus 164 dBc per Hertz. There seems to be a spur as you can see in the blue track above, but I'm not so sure. Anyway, it is significantly better than before, and better than 163.5. So that's down here. It's about where I wanted to go. So I will redesign the impedance transformer, this thing, these two toroids, to load this the drains here with about 1 kiloohm instead of 2 kiloohms. After 9 minutes only, it looks very promising. At 20 Hertz, minus 117, and that is with 50 decibels of carrier suppression, which means minus 167. I have to check that I really did everything right, and I will show that. Here is the oscilloscope view when the system is running and everything is balanced. So I go to the attenuator and insert 10, 20, 30 and 50 decibels. 10, 30, 50. And then I connect Z0. And indeed, I get the same level back. So it isn't a mistake, that's really magic. I cannot really explain why going above 2 or 3 kiloohms is so harmful for the performance. But I just I can feel satisfied that this is now not anymore a noisy amplifier. Well, this is not. The close range now, after a little more than 1 hour, shows very good results. I will take down the numbers and plot on paper. At close range, below 100 Hertz, there is some correlation between amplitude and phase noise, but at higher offsets they seem independent, uncorrelated, and they have a similar level. With the close range settings, I can see data up to 400 Hertz, and it was minus 183.5. Now I have set faster parameters, larger bandwidth, and so after 2 minutes I can already see at 400 Hertz something like minus 183. And I will have to wait for a while to see what happens at wider separations. 2 kilohertz, about minus 187. The flat noise floor starts at about 3 kilohertz and it is at minus 188.5. Here is what I've got. An almost perfect straight line from 0.5 Hertz all the way up to 50 Hertz. And then it bends slowly off towards the flat floor at minus 188.5. That's here. In the next video I will run a cable from this output to the input to make this unit an oscillator again. There are several things to experiment with. For example, the current through the FETs with this resistor, and how to tune this coupling capacitor and that one, if they should be tuned for similar performance of the two filters, or if one or the other should be made more narrow. And there are a couple of other little things to try when it runs as an oscillator.